Now we've talked about this before in our previous lessons, but just to review, according to the octet rule, atoms will lose, gain, or share electrons in order to achieve a noble gas configuration. Remember, this is the octet rule, so this is 8 because 8 is great. Atoms would prefer to have 8 electrons around them. So here we have the bonding scheme of F2. So each fluorine atom in F2 has 7 valence electrons, where one of those electrons in each of them is unpaired. Now, because both fluorines have 7 valence electrons and they're 1 electron away from having a full octet, or 8 electrons around them, what these two atoms are going to do is share those electrons so that they can each claim 8 electrons. So the fluorine here in red gets to claim these 8 electrons, and the fluorine with the blue electrons gets to claim those 8. The two that are overlapping between them were the unpaired electrons, but now they are paired up. Think of it like a puzzle, right? If you have a puzzle piece, these two are going to fit together and stay together and form a bond. So, only valence electrons will contribute to bonding, and this is specific for covalent bonding. Because fluorine is a nonmetal, so it's a nonmetal with a nonmetal, and if electrons are shared, that means it's a covalent bond. If electrons are donated, that is an example of ionic bonding, which is what we discussed in our previous chapter. So, since valence electrons are the only electrons that participate in bonding, we have to remember how to determine our valence electrons. So let's do a little bit of review from our previous chapters. How many valence electrons are in one oxygen atom? So I'm looking at oxygen by itself, only one oxygen. Look to your periodic table because our periodic table can help us remember how many valence electrons there are in each atom. If you find oxygen on your periodic table, you'll see it's in group 6, group 6A, or group 16, which tells us the number of valence electrons because our group number with the A after it is equal to our valence electrons. So, since oxygen is in group 6A, it has 6 valence electrons. Remember, if you're looking at the group number where it's in the teens, we have to take that number and subtract 10 so that we get our number of valence electrons. And if you think about it with oxygen, oxygen is element number 8, so it has 8 protons and 8 electrons. It simply cannot have 16 valence electrons because there's only 8 electrons in oxygen overall. So that's why we have to remember to subtract that teen value by 10, which is why it's also useful to look at the group number where it has the A after it. Okay, so let's quantify how our electrons are participating in bonding using the octet rule. So what we were talking about with fluorine F2 previously, only 2 of its valence electrons were participating in the formation of the F2 bond. So remember, just these 2 valence electrons were the ones that formed the bond. The pairs of electrons in a bond, or that form a bond, are called a bonding pair. So this pair right here is a bonding pair. And we typically show our bonding pairs in structures as a line. Our line represents our two electrons that participate in the bond formed between the two atoms. You can think of it like here's an electron, there's two electrons there, and we connect the dots to form a bond. So if the electrons are in a bond, they are considered a bonding pair. Fluorine had 7 valence electrons, but only one of them was a bonding electron, right? Only one electron came from each fluorine to form the bond. Therefore, the other 6 valence electrons were not a part of the bond formed. So we call those lone pairs. So the little dots of electrons on the outside of each of these fluorines, okay, since they're paired up, those are our lone pairs. And remember, we're talking about pairs. So pairs mean 2, so 2 electrons. A bonding pair has 2 electrons and a lone pair has 2 electrons. The lone pairs are just the valence electrons that are not participating in the bonding of that molecule. So to represent molecules where we show their bonding and their bonding pairs and their lone pairs, we can start drawing Lewis structures. And a Lewis structure is a representation of covalent bonding. Okay, this is only for covalent compounds. So this will be 2 or more nonmetals. We don't have Lewis structures for ionic compounds because they're not actually forming a bond. A bond occurs when there is electrons being shared. If the electrons are not being shared, then there's no bond being formed. And in ionic compounds, the electrons are being donated. So the two atoms are being attracted by their difference in charge. That is not happening here with covalent compounds. The electrons are being shared. Therefore, we have bonds, and that's how we represent our bonds is through a Lewis structure. So the shared electron pairs, so those bonding pairs, the electrons that are shared between the two atoms forming the bond, are shown either as dashes or as pairs of dots. So here we have water, H2O, and its Lewis structures. H2O has a bond from the oxygen to the hydrogens, and we show those with these 2 electrons here. I'll change color so it's a little bit easier to see. We have 2 electrons here, 2 electrons here. One of those electrons came from the hydrogen, and one of those electrons came from the oxygen. Okay? So these would be our bonding pairs. Okay? The lone pairs are shown as just dots on the individual atom. So oxygen has 2 lone pairs, which I'm highlighting in blue, that are just associated with the oxygen itself. Okay? So these would be our lone pairs. Our lone pairs can have another name, and that is non-bonding pairs. Because they are pairs of electrons that do not participate in bonding. So we show our shared electrons, our bonding pairs, as either dots or dashes. So here's those dashes. Let me represent them in red. Here's those again. Those are our bonds. And our lone pairs are just pairs of electrons on our central atom. We want to designate the difference between bonding and non-bonding pairs, which is why we typically show them show structures more in this fashion, where we show the bonds as dashes and the lone pairs as dots. So we can say that these electrons are in fact non-bonding, and these electrons are bonding. So I'm going to be drawing these structures for the remainder of this lecture outside of some of our practice problems in this form, where I have my shared electrons as dashes and my lone pairs or my non-bonding pairs as dots. Okay, So we also have to discuss multiple bonds, how multiple bonds are represented in Lewis structures. So in a single bond, which is what we have been looking at, the atoms are held together by one electron pair. So in water, again, here's that one electron pair that's holding together the two atoms or creating the bond. A double bond then has atoms that share two pairs of electrons. So I'm going to try to color code these. We have one pair on each side. For this is carbon dioxide, so this is CO2. Okay, so they have one pair on either side, and then they have another pair on the other side. So they are made up of two pairs of electrons, and those are both bonding pairs. So we have two bonding pairs that make up a double bond. We show double bonds as two dashes parallel to each other going between the two bonds. Okay, so we show them as a way to connect them. Again, think of it like there's 4 dots here and you're connecting those dots to form the double bond. So we draw them to connect the two atoms. And then again, our lone pairs are shown as just dots on the individual atoms. Our last type of bond is a triple bond. And a triple bond occurs when atoms are held together by 3 electron pairs. 3 electron pairs. So double was 2, triple is now 3, and that's where we're going to end it. We don't have any quadruple bonds or anything like that. We only go from single, double to triple bonds. So this is 3 electron pairs, so let's highlight those 3 electron pairs. There's one here, and then there's another one there. We'll use green to show our last one. So we have 3 bonding pairs that make up a triple bond. And we show triple bonds now as 3 parallel lines that connect the two atoms. Again, because it's like we have 1, 2, 3, 4, 5, 6 electrons that are participating in the bond. So they just connect those dots. Okay. So let's practice this. You'll see similar problems like this on your ALEKS homework. And what we want to do is using these Lewis structures where we show our bonds as dots, as well as our lone pairs on dots. As dots, we want to count our bonding and our non-bonding pairs. So what I'm going to do is I'm going to use my highlighter here, and I'm going to say anything that's highlighted in blue is a bonding pair. And anything that's highlighted in red is a non-bonding pair, also known as a lone pair. They're not participating in the bond. So these would happen between atoms, and these are on one atom. Okay. So let's do our first structure. We're going to try to identify our bonding pairs first. So we have CO2 here. So we have bonding pairs. I'll try to zoom in here. Is that going to be too large? It is. Let's get a little smaller. So we have CO2. We have a bonding pair here and a bonding pair there. That's between the carbon and the oxygen. On the other side, we also have a carbon and an oxygen. So there's a bonding pair there and a bonding pair there. For our non-bonding pairs, they're going to be localized on just the individual atoms. Carbon doesn't have any, okay? All of its electrons are in their bonds. So oxygen has 2 non-bonding pairs on each of those. So those non-bonding electrons are not in between the oxygen and another atom. They're just localized on the oxygen. So CO2 for bonding pairs has 1, 2, 3, 4 Remember, this is pairs, so we're counting by twos. And non-bonding pairs, it has 1, 2, 3, 4. We can always double check because we know that this is in total 8 pairs, which is equal to 16 electrons, right? Because each pair is 2 electrons. So we can count those up and say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 electrons that we are representing. So we have properly accounted for all of our pairs of electrons in this structure. So let's move on to our next one. Okay, it's a little bit more complex, so let's just go in and start figuring out our bonding pairs. So in blue, I'm going to highlight any pairs of electrons that are between atoms. So let's start from the left. We'll go between oxygen and hydrogen. There are 2 electrons that are shared between those 2 atoms. On the other side of oxygen, between oxygen and carbon, we have another 2 electrons. And then after carbon, in between the next carbon and oxygen, is another 2 pairs. The pair over here is not in between an oxygen and another atom, so it is not a bonding pair. Above the carbon, we have some pairs between the oxygen and the carbon. So we have a pair here and a pair there. Okay. Next up, we're going to look for our non-bonding pairs, and those are going to be the pairs of electrons that are not in between 2 atoms. So that's every other pair that we see. So oxygen has 2 pairs that are localized on itself. The other oxygen on top here also has 2 electrons. And our oxygen on the very end has 3 pairs of electrons. So let's count those up. Our bonding pairs, we have 1, 2, 3, 4, 5. And our non-bonding pairs, we have 1, 2, 3, 4, 5, 6, 7. Let's just double check our work. 5 plus 7 is 12 pairs, which should equal 24 electrons. So let's count those up. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We have all of our 24 electrons accounted for. Awesome. Let's do another example. Okay, again, let's start off by finding all of the electrons that are in between atoms. So in between the carbon and the hydrogen, there's pairs on both sides. And in between the carbon and the oxygen, there's pairs on both sides. That's it for our bonding pairs, and our non-bonding pairs are just localized on the oxygen. They're not in between any other atom in that oxygen. They are strictly around the oxygen itself. So our bonding pairs, we can count up. We have 1, 2, 3, 4. And our non-bonding pairs, we have 1, 2. Okay, so that's a total of 6 pairs, which is equal to 12 electrons, which we can count up and see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All 12 electrons are accounted for. So we should always double check our work. Okay, so we have 2 more examples down here. Let me highlight them here. Oops, highlighter's too small now. There we go. We have these 2 examples down here. What I want you to do is pause the video and try these last 2 examples on your own. Okay, let's zoom in and see what we can do for each of these. I'm just going to erase some of this so we can highlight it. Okay, so let's start off by looking for our bonding pairs, and those are going to be the pairs of electrons that are between our atoms. So we have a pair in between our carbon and our hydrogen. And then on the other side of carbon, we have three pairs of electrons that are between the carbon and the nitrogen. For our non-bonding pairs, we just have one on our nitrogen there. So let's add these up. Bonding pairs, we have 1, 2, 3, 4. And for non-bonding pairs, we just have 1. This is a total of 5 pairs, which would equal 10 electrons. So let's check our work. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. And let's jump to our last example over here. Okay, so let's count up our bonding pairs first. We only have 2 atoms in this molecule, so it's any pairs of electrons between those 2 atoms of nitrogen. So we have 1, 2, 3. Those are the only pairs that we have in between our nitrogens. On the opposite side of each nitrogen, we have our non-bonding pairs. So in total, we have bonding pairs 1, 2, 3. And our non-bonding pairs, we have 1, 2. We should always check our work, so that's 5 pairs. That should be equal to 10 electrons, which we can count up and see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. Awesome. So we can see through these molecules that we can identify our bonding and our non-bonding pairs. In many of these, we saw our multiple bonds. So here we have some double bonds. Okay, we even had a double bond here. Here's another double bond. We also had some single bonds. We have multiples of those in that molecule. Finally, in our last 2 examples was where we saw triple bonds. Because we had 3 pairs of electrons holding two atoms together. So there were 3 pairs of electrons in between those nitrogens, so they make a triple bond, which we also saw over here between this carbon and nitrogen. We have a triple bond. Okay.